Now, there are times when integration parts can be applied, but there's no product of functions that's explicitly stated, and this is really a special use case, generally involving trig functions, inverse trig functions or logarithms. And the reason this is the case is because when you use the integration by parts, you have to pick a u and a dv. So the thing is, you have to have a function where u would not be the algebraic piece, because you can technically say that any function is the product of that function and 1. So the algebraic piece would be 1, and then you would have the logarithmic piece. According to ILATE, the logarithm, it gets chosen before the algebraic piece. So that's important. So we will choose u to be the natural log of 2x, and dv to just be dx, so that du, the derivative of the natural log of 2x, if you go off to the side, just remember the derivative of a logarithm, so the derivative with respect to u, or sorry, I should say with respect to x, of the natural log of some function u of x is just the derivative of u over itself. So that in this case, that would be the derivative of 2x is 2 divided by itself, which is 2x. So that results in 1 over x dx. Then dv, when we integrate that, we end up with v equals x. Okay, now applying integration by parts, let's see what happens. So I have u times v, so x natural log of 2x minus the integral of v du. So v du in this case would be x times 1 over x dx. And the nice thing about that is x and 1 over x cancel each other out. So essentially I just have x times the natural log of 2x minus the integral of dx, and that's a relatively simple integral to perform. It results in just x. So we have x natural log of 2x minus x plus c. All right, another case where that can work is with, like in this example, arcsine of x. And the process is basically the same. You have two functions multiplied, but one of those functions just happens to be the constant 1. So you don't want to pick 1 to be here, because when you take its derivative, you get du is just 0. So that's not going to work. But in this case, according to ILATE or LIATE, whichever you're using, inverse trig functions come before algebraic. So we could pick u to be the arcsine of x, leaving dv to be just dx. Now du, this is a formula that you have seen from Calc 1. You might need to refresh on, but the derivative of arcsine, if you'll recall, is 1 over the square root of 1 minus x squared dx. And dv, its integral, we would get v equals x. Okay, so this will become u times v, so x arcsine of x minus the integral of v du. So x over this square root 1 minus x squared dx. Now, in the last example with logarithms, this integral became much easier, but in this case it's looking like it's rather complex. In fact, you might be thinking that you would have to actually use some sort of trig function integral in order to perform this. But as it turns out, you can actually use u substitution here. If you just let u be the part underneath that radical, then du is negative 2x dx. And then what you can do is rewrite this as x arc sine of x. Let's see, I guess I'm going to need to divide this negative 1/2 over, okay, so that this would actually be plus 1/2 times the integral. And all of this gets replaced with 1 over the square root of u, which would be u to the negative 1/2 power. And I skipped a couple steps there, but if you need to see them, you can kind of go off to the side and sketch them out. I think you can handle it at this level. Then we have x arc sine x plus 1/2. The integral of u to the 1/2 power would be u to the 1/2 over 1/2 plus c. And this actually ends up being a multiplier of 2, which cancels with the factor of 1/2 over here. So we have our final answer, which is good because I'm pretty well out of space. That's going to be x arc sine x plus, and then u was 1 minus x squared, and I know that I used u in this case and u in this case. You can switch and use a different variable name if you like, but as long as you understand your own notes, that's fine. And this would be the square root of 1 minus x squared, and finally plus c.